First of all, thank you for coming, and thank you to the SUSE guys that invited me here to speak. I'm Alberto Galli. I work in EMEA. I'm an HPC consultant, and I work mainly, of course, in the HPC, but HPC is a sort of framework in which the storage is gaining a lot of interest. And the experience that we are going to share this morning is an experience that we have a customer side. I cannot name the customer name, but anyway, it's an oil and gas company at the end of the day. Being an Italian guy, you can easily find it out. Okay? It's not a big deal. Okay, let's start. Okay, this is a sort of agenda. I apologize for this slide, but I'm using these slides in several places. And I know that you know better than me what an object storage is. Most probably you don't know what DMF is. So let's go for the Ceph part. DMF is a hierarchical storage management. Means that you have a tier that normally is pretty expensive, and you move out the data somewhere else. The beauty of this kind of tools, I don't remember the slide, so, well, let's say, maybe I can repeat one part of those things. From the user experience, what you see is that your file is still there. If you issue an LS, you see the file there. Actually, the file is not there. You have a stub. So everything is moved somewhere else, but from the user experience point of view, you see it. That's easy to use. If you touch the file is recovered immediately. Depending on the speed that you have on the back, you don't even notice that it was somewhere else. There are many features about DMF. Anyway, let's go. This is the framework, the general framework. DMF is this is a point that must be, I will come back on it later, but I want just to introduce a few concepts. DMF initially, historically, was moving data, okay? Meaning I have a file, I copy the data from here to there. The scope now has changed a little bit because they take the metadata out, and these have some benefits. And there is an example later on. But anyway, just to give you a quick overview, if you take the metadata out, you are free from the front end where you're getting the data. And you can even change the front end and deploy the data somewhere else, on a new storage, on a new technology, or whatever. Because you have all you need in order to rebuild the status of the file on top of the new storage. I will come back later on that. This is the general idea, just a few words about that. Architecturally speaking, we have a database where you have a sort of snapshot of what the file system is, or the file systems are, and then you have parallel movers. The parallel movers goes without saying, they are just moving files, and different backends. This is the idea that is behind, I lost the pointer, oh, okay. DMF works in this way. What you are doing is you're scanning the data. Actually, you're scanning the file system. So you have a copy of the file system, okay? So you know exactly what you have on the file system. So you capture the metadata, indeed. What it does is move, DMF can move automatically the files. You can use policies. You can use position, you can use tagging. You have a lot of possibilities in order to make the movement happen. For instance, imagine that you have a customer, and this is somewhat the case, in which you have some files that you are working on, some files that you are not working anymore since long because I don't know, the project died along the way. Some files that you have to back up because this is the copy of something that has gone in production. You can tag the file. You say, okay, I want this file to be backed up, and this will go to tape, for instance. I want this file to be on top of my Lustre storage because I need to do some calculation using some specific package. I can tag the file, it will be moved somewhere else. This is an old file, well, just archive it. I don't want to throw it away, but I want to archive it. Okay, fine, it will move. Okay, so you have several policies to do that. This is another example of what's just a real, quick explanation about this stuff. I mean, think about you have a limited space of storage as a tier 0. Just to name it, there is Weak.io. Weak.io is very fast, but pretty expensive. So you cannot buy 10 petabytes of stuff. You can buy some storage. So you cannot think to use that storage in a traditional way. You have limited space. So you can ask DMF to do some work for you. For instance, I launch a job. I know that I need this file. What it does is, well, with the help of a job scheduler, it says, okay, I build a file system on top of this highly and expensive storage. I copy the data inside there. I run the job. I take back what has changed in the meantime. I destroy the file system, and that's it. Next job, please. So DMF is going to do all these kind of things. And this is an example. So this is what I was saying. Sorry, I need to fly because the guys are pressing me. They need to speak after me, so I need to fly. I feel some pressure here on my neck. Okay, going to the customer case. This is this is kind of interesting case that we had. This is the framework, and this is the idea. Why DMF came into the picture inside there. This is a cluster. Well, we have 2 clusters, okay? And the tier 0 is shared between the 2 clusters. So you have some routers in order to access the very same file system. Traditional approach, really traditional approach. This kind of approach is around in that company since 10 years also, maybe 9. But anyway, that's their way to do it. Data sharing, high speed required. When I say high speed, we are speaking 240 gigabytes per second. So it's not really something that you find easily. What's the problem? The problem is that tier 0 being so fast, you can use a few technologies that are on the market. One is Lustre, the second one is GPFS. Third one can be BGFS, but anyway, that's it, end of the story, okay? Those guys have one thing in their mind, performance, only performance. Reliability, okay, not so much, because we need to go fast. We have a case where we have 1 petabyte per second. That means that you have to go very fast. So you have some reliability, but you can't sleep during the night if you are storing data on top of that boxes, because it can be lost. It's not aimed to do that. So the solution at the end was, well, we introduced a tier 1. Okay, the problem is now how to move the data automatically between the two. One idea, sometimes it happens, especially with small customers, they are doing it manually, but it's not really something that you can do easily. Those were the customer requests. So 200, you can see 2 petabytes, actually petabytes, that is roughly 12 or something petabytes. And good amount of I/O per second, not really too much, but anyway, for the kind of technology that we are looking for, the Luster, that's pretty enough. And a tier 1 in which they wanted to have access S3, blah, 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 blah. The problem is that they want to have a tier 0 and tier 1 from the same provider. Okay, you must know, if you're not familiar, the providers are 2 in the world. One was Seagate that actually has been bought by Cray. The second one is Data Direct Network. End of the story. The third one was NetApp that acquired LSI Logic a long time ago, but it's somewhat out of the game now. So just 2, that's easy. So what we have done, the problem was that we had GPFS. Going pretty fast, what we did was to change, and we had introduced Luster. That initially was a sort of nightmare. And we used what is called H200. H200 is an object storage. And now you will see the, the story.
Oh, was.
Okay.
Could you just very briefly tell us why Luster was a nightmare?
Luster was a nightmare because we made a POC, you will see. And the problem is not Luster itself. The problem was the way the customer was used to have access to the file system within their own application. We had to change between GPFS and Luster. And initially we had some problems. We solved all the problems, of course, but it took a while in order to make it work. So it's not a technology problem.
Maybe to add to Alberto's comments, I think the customer was using GPFS for a long time.
Yeah.
It's like all technology, when you have a customer that's using a technology, change it, on the paper it's the same technology, it's POSIX. Yeah, but in reality it's not. Okay, so everything was broken. So you have to relearn. Actually, the problem is actually to teach the customer how to change the way to do things. Okay, that's.
HSM, in order to make the movement, Robinhood and copy tool. Okay? And, well, some lessons maybe can be. We didn't test. We made a long POC on Luster, but we never tested Robinhood and copy tool. You will see now in a moment. Okay, and now what happened? That H200 was retired from the market. Suddenly, out of the blue, one day we discovered that Seagate decided to give up on Luster. The Luster part was acquired by Cray, and the H200 they marked simply as end of life. It was a nightmare, really, in those days. So we had to decide what next. And what next was DMF. DMF at the time was not ready because it was the old version. Now we have DMF 7, it was DMF 6. We didn't have a backend as an object storage. We are using DNE on the last metadata, and it was not supported. And Robinhood and copy tool was inadequate. We had a lot of problems, daemons disappearing, dying along the way. So it was really, we never understood honestly where the problem was, inside the H200 or inside the Robinhood. Anyway, that tool wasn't working for us. Okay, the solution was using DMF. Again, going back. So at the end of the day, what is happening is that you are putting DMF in the middle, you have Luster on top here, and then you have backend, specifically object storage. That's why we didn't go for Ceph initially, from the day one, or day zero if you like, because they wanted to have everything provided by one single solution provider. That in our choice was Seagate, actually Cray. We decided to go for Ceph. Well, I'm not going to spend too many words on that. I mean, you know very well what Ceph is. So, easy. We had still some question marks about that, that we have to solve, but the problem was exactly this one. I mean, or excuse me, the solution was exactly this one. We brought all the people around the table, DMF team, our engineering team, and they made a very good job because they took their own roadmap and decided to align the roadmaps to some customer needs. The second point was, well, we had to manage some availability issues. We got in touch with our SUSE friends, and we got a lot of help in how to characterize the backend. The problem about the backend was about the 10 gigabytes per second. No one knew at the time if you were able to reach 10 gigabytes per second with 5 petabytes in front. So Darren from SUSE was the one that helped, especially Cedric, in order to make it work. Last but not least, our competition. But anyway, Cray, they're pretty friendly. I'm working almost every day with the guys. And they made a part in some bug fixing on the HSM part in order to have DMF working. In other words, that's teamwork. That's what I have learned the hard way along this journey. It's not the very first time. You cannot solve this kind of problem by yourself. Those are solutions. Those are not products. Those are solutions. It's the chain that works. If something doesn't work along the chain, customer is gonna kill you because you are managing the chain. They don't care about the luster being a problem. The fact is that the functionality doesn't work. Where the problem is not their own problem, it's our problem. So you have to work in that way. And so now, finally, we have this solution that is based on DMF. This is the architecture that I put just for your reference. I'm keeping saying, please, 10 seconds of commotion, because this is the version 7. I was the one that that made all the drawings 7 times. You can lose your eyes, okay? So. And now, well, DMF, let's go back for a while. You remember, well, we are doing the change between Luster and GPFS. The problem was we need to move the data while the production were going on. We didn't have the possibility to stop the production. The system were in production. So, one copy only. So we carve out 10 nodes, mounted on GPFS, move the data from GPFS to these nodes and back to Luster. Easy, right? Pretty easy. This is the problem. It took a huge amount of time. Because you always find at scale problems. When you are going at scale, you have problems. No way. You have something that suddenly stops, you don't know why. You can't understand why. And so that's a problem, okay? If I could have had DMF, would the thing be different? The answer is yes. Because what you can do with DMF, if you remember what I was saying initially, you are taking away the metadata. So what you can do is just destage the files. That means you are copy the files, including the metadata. You store everything inside there, inside the Ceph, and then you change to Luster and you do a stage. So you don't do anything but stage and destage. And DMF is being engineered for doing that, staging files, destaging files, moving files, copying files, archiving files. You have several copies. On the back end, we have 9+3 erasure coding, so we are in a safe position. We have 2 copies at least, one on the back end, one on the front end. And it's not a tool that is just moving data using some sort daemons here and there and so on and so forth. And the next point is what I was saying before. DMF can be used for even different things. Now we are evolving this customer is acquiring new equipment in order to make some AI at the end of the day. And part of the file are here. Part of the file, not all the files. So they are going to buy a new small cluster compared to the other guys. And we need to have somewhat an idea on how to move the data between the two. And DMF can be handy on that because you can do exactly the way I was saying before. You tag the file. You say, this file, I want to have this file on both the storage. So you tag the file on here and say, okay, this is a file that I want, I don't know, the image or whatever it is, and I want to have a copy over there. And DMF will do exactly this kind of movement. Well, it's stored on the back end and put on the other side. It can be almost immediate, depend on the speed that you can achieve on the back end. So DMF is very handy on the stuff. And Ceph plus DMF is very useful to have Ceph on the back end for several reasons. First of all, it's open. You can have a lot of protocols. One idea that this customer has is using the backend that is just Ceph for doing something else, not just archiving. Because we have S3 gateways, but they can open to NFS, to whatever they like. I mean, it's just a matter of putting some gateways on top of that. The second point is that we are saving space because we are speaking about 5 petabytes. That means 7.9 petabytes. Pretty huge, 3 racks, 700, almost 800 disks, 12 terabytes. By being 9+3, we can save space. Imagine that you have to maintain 2 copies or 3 copies. It's a huge amount of space. So Ceph is exactly what we were looking for. It's open, and at the very same time can help you to save space. That is money, because anytime that you are putting something on the floor, they pay something for that tile that they are using. So we need to squeeze out the things pretty badly. And this is, I think that this is my last, slide on this topic. And well, I leave you to read, and in the meantime, I leave to Alessandro, right? Alessandro that is gonna take over. Thank you.
Can you give me the pointer? Okay. So just a few words about SUSE Enterprise Storage, and just to remember what was the goal of the customer. The requirements was to have a backend object store around 5 petabytes just to start, and the performance were important, very important, but most of all, this is a production system. Very important production system for the business. So the resiliency, the viability, the robustness of the solution was key to select the right backend. That's why SUSE Enterprise Storage was the best option, because it was something at, I would say, enterprise level of quality and support. And we had, as Alberto said, a lot of benchmarks, proof of concepts, and we had to find a clear design in order to find the right combination of hardware and tuning for the Ceph part, okay? So what is SUSE Enterprise Storage, for who doesn't know? It's a software-defined solution based on Ceph technology, open source Ceph technology, that has a lot of nice features. It scales really well. It can use commodity hardware, so you can use x86, 64, even ARM hardware. It's resilient, it's self-healing, it's a cluster that can scale at a very huge number of nodes and storage. And if you look at the architecture, the core is reliable, autonomic, distributed object store. At the end, this is an object store that can scale to thousands and thousands of nodes made by different kind of disks that you can select in order to achieve what you want, in order to have the right space, the right protection level, the right performance, and whatever. But one of the most important things about Ceph, about SUSE Enterprise Storage in particular, is that SUSE developed a very large way of accessing the storage, because this is an object storage at the end, but you can access the data using block device protocols. You can use iSCSI, you can use native RBD, Rados block device, if you want to use that. You can use pure object storage, like S3, that's a standard. In this case, we use S3. You can use a file interface, CephFS. So you can really use this solution for any kind of implementation, okay? And what SUSE did in the last years and what is committed to do is to improve the way of managing the solution through many tools and many different parts of the technology that are part of the solution, the end solution. One of these, for example, is ease to deploy and to manage, to configure the cluster using, in this case, a very nice graphical user interface, web-based, using OpenAttic, that, by the way, now is the upstream way of managing Ceph in the community as well, okay? We made a very, very good work in that. So as I said before, the anatomy of the cluster was made by several nodes, and in this particular case, we used S3 gateways, 6 gateways, if I remember, right? Okay, but after that, Cedric will show us the exact numbers. And in order to have the scale and the performance needed in order to achieve what was the customer needs and the customer objective. I think that I can pass the mic to Cedric.
That's okay. Have the mic.
Okay.
Have a mic already. So first of all, we're a little bit in advance. We have some time. So are there any questions about what was presented by my colleague Alberto or Alessandro? This is the time. Yes, two questions actually. So please, go ahead.
I suspect that you'll not be able to answer this in any great detail, but trying to get to that very significant number of 10 gigabits per second throughput, can you characterize in some way what?
I'll talk about that later on. I mean, what's remained there? Okay, first, before you ask a question, the remaining of the presentation will be about how to make sure, or we made sure that we were able to attain the required performance. Okay. So that's about that. That's again mainly about Ceph. Any other question regarding the cluster, the HPC, the more generic things about moving data around, and et cetera, and et cetera? No? Okay. That was your chance. Last one. Okay, so let's go on. So as Alberto said, so we have this great opportunity to deploy a Ceph cluster, SUSE Enterprise Storage cluster at the customer side, but we had to make sure that we were able to reach the performance. So for that, there's only way for me to do that is to do POC, to do testing, benchmarking. I mean, I'm coming from HPC. I think 50%, well, actually more than that, 70% of my time is spending in benchmarking, okay? I don't like spec sheets about products. I like to test them and make sure that actually I can reach the numbers, okay? If I cannot, then that doesn't mean anything. So at that time, well, actually, we still have it. We do have a cluster. There is an echo over there, so I'll move. Okay, I'll move here. Can you still hear me? Yeah, that's perfect. Okay, we had we still have a Ceph cluster dedicated for benchmark. Okay, SUSE Enterprise Storage cluster dedicated for benchmark. So yeah, if you hear Ceph, and I'm sorry about my SUSE people here. This is a SUSE Enterprise Storage cluster, okay? But anyway, it's based on this hardware. I don't want to go to too many details because most of them it's irrelevant to what we did here, but we do have Apollo 4200 Gen 9. We do have some SSDs part for block, which were not used at all in that project. And we have Mons on some gateways. What you have to remember for that is, first of all, we're using 100 gigabit Ethernet backend. So what you have to remember is, so this hardware is still available. We still can do benchmark. Actually, I'm engaged in a new one recently. So it's basically POC for customers. That's very valuable for Ceph because I don't know if you attended some of the talk yesterday, especially the one with David Bites. We were saying that actually we need, I mean, there are a lot of use cases for Ceph, and we need to do some benchmarking in the end to make sure that we can reach the performance. Okay, this is here for that. So this is on HPE hardware, so it's better to sell HPE hardware after that. I'm here for that. But yeah, it's still available, and if you're interested to run some POC on it, just let me know. I'll let know our SUSE colleague now that will put us in contact. Anyway, so we did use that. Yeah, one thing we wanted to make sure is, as we said, is to be able to reach the performance. Okay. So there is actually a mistake, spelling mistake in that slide. I've never seen that before. It's a new one. So you should read CephFS, not CephFW, which is firmware. I don't know what it is.
It's only for Friday. It's a good product.
Yeah, let's say that. So we tested CephFS. So you asked me why we did test CephFS because we're about to use S3. That's a long story. I can go into that. But let's say we had to test CephFS just to make sure that we're able also to reach the right numbers to achieve. So we did that. I was using, so for those who are from HPC, they must know these things. We're using IOR benchmarking. So it's a nice tool that actually writes and reads in parallel. This is basically what is used in huge cluster benchmarking parallel file systems. So when you see, if you go in the top 500 list and you see some systems that are able to do 500 gigabytes per second, they're using IR to test this. Okay, so the idea was to use the same tool for Ceph to basically find out what were the performance we'd achieve. So we were only using spinning drives here, so no SSDs. As you can see, we test across. So all the tests were done over Ethernet. I've tested several parameters. So first of all, single threads, then adding additional threads, then using read ahead, that's for the picture to see if it was impacting the performance, and also read. And this is the performance we did get. So just to give you an idea, so I do have 6 servers, so 6 Apollo 4200s. Each of them did have 16 drives at that time, actually 15, because one drive was used for the boot, 2 NVMEs, and I was able to reach writing 7 gigabytes per second, which is pretty nice. Actually, sorry?
How many disks?
Well, 15 times, yeah, 15 in every node, so 15 times 6. And I did use, I think I was using 6, it's written somewhere, no, 9+3 erasure coding. Okay, so, well, if you ask me, how do you do 9+3 when you have only 6 nodes? Well, it's a hack. I mean, it's not something you have to use in production anyway. It was just to test the whole overall process protocols and see how it was scaling. Okay, typically, at full performance, every drive were delivering around 40 megabytes per second. Okay, you could see that looking at what's going on drives. So, yeah, coming back to our overall goal, I mean, with only 6 servers getting 7 gigabytes per second, that's a good sign. Because as you'll see, the end solution is based on how many servers again? 24. So should be okay. But yeah, well, at the end, we knew that S3, well, no, so CephFS was not the solution. I mean, DMF need S3, so we need to do S3 test. More than that, we actually need to do DMF test on it, okay? So the second part of the POC, that's also happened in Grenoble. We basically installed DMF, so that was the help of our engineering. On test basically what was the maximum performance we did achieve. So we tested DMF v6 on DMF version 7. Okay. I don't want to go into too much details because first of all, I don't exactly know what were those parameters. Okay, that's the DMF internal things. I can guess. That will not be interesting. The most important thing is, as you can see, so we're using S3, we're using 2 gateways. That's important because as you may or may not know, when using Ceph on accessing an S3, you need gateways. You may be limited by the gateways because the gateways have a maximum bandwidth, okay? So using 2 gateways, we were able to achieve, I think it was in writes, well, 6.5 gigabytes per second, okay? Still using the same erasure code, okay? That was with DMF version 6, okay? Interestingly enough, with DMF version 7, which is the one we were interested by, we're not that good, okay? With 2 gateways, we're around 4 gigabytes per second. I think at one point they changed that and they were able to achieve 2 times that. But yeah, that was basically the idea, okay? Yes, question?
I'm sorry. On the bottom it says there should be a
Oh, that's wrong, we're on good way. Yes, go ahead.
a purple get metric, but is that just missing or?
That's missing, okay, because we did not have the time to do the get, okay? So that's only right. And actually, okay, I was wrong because this was done with 1 Redis gateways, okay? So we're able to achieve 4 gigabytes per second. So 1 server were being accessed with the writes. Okay, so what we learned during this first POC, first of all, that we're now sure that Ceph or SUSE Enterprise Storage was the viable solution, okay? With a very small solution, we're able to achieve 7 gigabytes per second on CephFS, yeah, 4 gigabytes per second with 1 Redis gateway. So being able to achieve, well, something around 8 gigabytes per second if we wanted to go there. DMF on Ceph was also a viable solution, okay? So we found some limitation in DMF, but well, still, the 10 gigabytes per second were achievable, okay? We also had the basic configuration. The one main idea around all these POCs, and after that, as you'll see, is we decided to not go too far from what we had, okay? Because we had the right hardware. Well, we knew hardware configuration that was working, so we wanted to stay close to that. Also on the software side of things, or the configuration side of things, we already knew something that worked, so we wanted to stay close to that. So erasure coding scheme, we knew that, network infrastructure, and et cetera, and et cetera. Okay? So we went for erasure coding 9.3, network infrastructure. We did separate public and private. So in Ceph, we can have both. We decided it was better to separate that to have the best performance. Also, we did use NVMe during the testing, and we saw that NVMe was important. So basically, NVMe is basically used here for the RockDB database on the write-ahead logs, okay, of BlueStore. This is the backend of Ceph. Okay, you don't have to use it, but if you don't use it, well, Darren, correct me if I'm wrong, but that's 75% loss in performance. Okay, so it's a good thing to have it. For the story, when we first installed this cluster with Darren, we did not have enough NVMe. The performance was not that great. So, well, we found out that one Rados gateway is capable of 2 gigabytes per second with DMF. So, yeah, we basically had the right numbers. So, now we have to choose what kind of configuration. So if you go onto, well, either SUSE or HPE side, when you look at the reference architecture, the two platforms that are listed are either Apollo 4200, well, now Gen 10, but at that time it used to be Gen 9, or Apollo 4510, Gen 10, yeah. Well, we decided, because we don't like to follow documents, we decided to go for a third one. Now, the thing is, Apollo 4200 was too small, okay? Which means we had to have too many of them, which means in turn that the network was too expensive, okay? Because the network, we went for a non-blocking network, okay? So basically, it's 25 gigs networks, and it's completely non-blocking. And that's expensive if you need to go with too many servers. Okay, but basically the number of switches required was awful. And also we have another problem with scalability. So adding more servers, if the customer wants to scale it, that means still adding more switches. It's not a good thing. Apollo 4510, so it's 4U machines, can go up to 60 hard drives. It's a nice machine. The problem is it has only 4 PCI Express slots. A little bit short. That means you have to choose between network. Well, yeah, we have to fit in network. We have to fit in NVMEs, and we have to fit in the controller, the hardware controllers. So you can use the 4510 though, but in our case, we really wanted to make sure we were about to reach the performance. So we wanted to have 2 hardware controllers, which is not mandatory, but it's better. We really wanted to have NVMe and not SSDs, okay? On basically 4 slots, 4 PCI Express slots was no-go, okay? So we invented this solution, which is a nice one. I love it, actually, which is based on the L380s. So I think this is the most sold server out there, connected to JBODs. Okay, so we have a nice JBOD called D6020. If you're interested by it, hurry up, because it's almost end of life, end of sales, not end of life. So it contains up to 70 drives, and it's basically divided into 2 separate JBODs. So if you have this big box, it's actually 2 JBODs, 2 domain with 35 drives in each. And the idea is to connect each domain to one DL380s. You end up with, if you couple 2 DL380s and 1 D6020, you end up with having 2 servers, each of them having 35 large form factor drives on being connected via SAS connections. Okay, very good one, because it brings us a lot of additional stuff. Since we're using the DL380s, we have a lot of space for, well, CPU and memory, but that's not a big issue. First of all, we can have up to 8 PCI Express slots. So if you want a lot of network, a lot of stuff in the back end, you can have them. And also, we can have a lot of NVMe in the front end, okay, if you need to. So that's a good thing. Well, actually, I already talked about that. It's just what I said. So we end up with this solution in the end, that this is what we sold to the customer. So as you can see, there is one rack, one rack which contains, let's say, all the service part of Ceph or SUSE Enterprise Storage, so the management node, the monitors, we needed only 3 monitors, 6 Rados gateways. Remember, we found out that, well, one Rados gateways was able to reach roughly 2 gigabytes per second, so having 6 of them on the correct scalability would lead us to 11 to 12 gigabytes per second, so we should have been okay. And 24 OSDs, each, well, basically split in 12 cells, so with 2 DL380s each and 1 D6020, okay? And that fits in, how many racks again? 4, 3? I don't remember. Oh, it's here. Sorry, cannot see it. 3 racks. Yeah, you see it? Yeah, in case you've not noticed anything, everything on the drawings, you can see it. Sorry?
Show the network.
Yeah, the network. Do you want to comment some stuff on the network?
Yeah,
no?
So the network, this is a topic that yesterday during the presentation was quite interesting because we spent a lot of time on the network. And this is an example. Of course, you can't understand from there, but in principle, those are the USDs, 24. Those are the monitors, forget about that. This is the public network, and this is the private network, and these are the gateways. These two are connected 25 gig everywhere, double connection, LICP in order to avoid to have a single point of failures. And you go up with 100 gig up to this core level. This is going to give you full bandwidth everywhere and full coverage from fault, because all these guys are connecting in what is called, well, depending on the technology you are using, you can have different names. This in this case is MLAG. That means a virtual. This is a virtual switch. So you are bonding. You are creating a bond between these two parts, so they are trunked together. You can have several of these, IRF, VPC, whatever. But the main reason, the main topic is that you need to have something like this in order to avoid any single point of failure. This is just replicating down on the private network, with the exception that on the private network you don't need a core level. And the reason why we are going 100 gig on this spine and 25 here is because we need to have full speed from the gateways to the spine level. Yeah. Because we have 100 gig on top of there. Yeah. Again, when you see two, because of mainly for failover reasons, not for speed. But anyway, you can even think to have some speed, well, not too much about that stuff. But that's why you have to think twice about the network. That's really important. That's the key part, really the key part of all the story. Of course, what Cedric was explaining is evolving mostly around this part. But this part is very important, absolutely important. If you're losing speed here, you're done. You're completely dead. And you will see now.
One additional thing. So first of all, I did completely forget about that. So in the network, we did have a public and private, but it was completely double. So the private network, every node was connected to, every OSD was connected to the private network with 2 links. On the same, every OSD was connected to the public networks with two links. So it's completely redundant. So in the end, that means you need to connect to a lot of ports. A little word about the 100 gigabits, because we had a lot of discussion about that. Why 100 gigabits? is because, remember, during the POC, we were using 100 gigabit networks everywhere. We're not sure that the gateways, the routers gateways, were able to achieve the same numbers without having that network. So we decided to stick with that. On the back end, we went out to 25, saying, yeah, we won't need the full performance anyway. We have some overhead here, but yeah, we wanted to be on the safe side for the routers gateways, and also the data movers and etc. So we wanted to not to have limitation from network perspective. Okay, so we did implement that. That was last July, July of last year. At that time, we had the opportunity to actually, we did install the SUSE Enterprise Storage Cluster. After we installed it, I have opportunities to run some actual S3 benchmark just to make sure that we reached the correct performance. So that was interesting for that deal. That's also interesting because that was my first opportunity to run such a benchmark on a big production, which was not in production yet, but soon to be in production, SUSE Enterprise Storage Cluster with a sizable capacity, which is 7 petabytes or 6 petabytes usable? Five usable? Okay, I thought it was a little bit more. Anyway, so I did use our CAS bench. So for those who don't know, this is a benchmark thing that's been written by Intel in the first place that basically allows you to send in parallel S3 requests. Okay, so it could be get, put, create, whatever. And you can measure the numbers. Okay, so what I did is I run the benchmark against 1 routers gateways, 2 routers gateway, 4 and 6. Okay, and look at the performance. I see here the performance is going for 5 gigabytes per second up to 30 gigabytes per second. Okay, and this is the number of so thread working per gateways. And as you can see, using 6 routers gateway, I was able to achieve something a little bit north of 25 gigabytes per second. Okay, very interesting. In read, that was a little bit lower. No, that's still right. So what's the difference? Yeah, that's it, right. Oh yeah, this one was more production ready. So it's basically I was running benchmark, writing and reading at the same time. Okay, which will happen in production. So I wanted to make sure that in real production, when you're reading and writing files at the same time, we're able to achieve the performance. On here, even with that, I was able to achieve a little bit north of, actually, a little bit south of 12 gigabytes per second in total. What we found out, one of the conclusions, so first of all, first conclusion is, okay, we're good. From SUSE Enterprise Storage perspective, we can achieve the 10 gigabytes per second, no problem. The second one is actually we are limited by the number of gateways. If you look at the scalability between gateways, it's been going from 1 to 2 to 4 to 6, basically we still increase performance. So the conclusion is actually the backend is capable of far more than that. So we're not able to know what performance we can achieve in the backend, but we know we have some room. If we have some problem here, we just need to have some routers gateways, and we'll increase the performance still. Okay, but we have some rooms. I do think we have a lot of rooms. Okay, so don't know where, but until what, but maybe 40 gigabytes or whatever. But that was very interesting. Okay, so this is done. So the project is now in production. So everything is running. Performance is all right. And yeah, this is it. Any question? Oh, there is no one? Oh, thank you. Yeah.